Lesson B. Rational expressions and equations without factoring. Okay, before we get into this, why don't we take a moment and just understand what this title is all about? What's going on here? There's actually a lot of info or whatever to sort of unpack out of this title. First of all, we're talking about something called rational expressions. What's that mean? What's a rational expression? And by the way, and equations. What's a rational equation? What's that? Well, the first thing, let's make sure we're clear on the difference between an expression and an equation. You see this? It's not an equation. It's not an equation. You know how I know that it's not an equation? That's supposed to be a It's not an equation because equations have equals in them. That's why we get equations. It's supposed to be two sides that have an equals. There's no two sides here. There's no equals. It's not an equation. So if it's not an equation, that means a couple things. A, please don't call it an equation because it's not an equation. And B, don't say that we're going to solve it because there's nothing to solve because it's not an equation. So let's actually write this out. You cannot solve this. It's not an equation. Only equations can be solved. I mean, what does it mean to solve? To solve means to figure out what x is, right? How are you supposed to figure out what x is? You have no idea what you're supposed to set this stuff equal to. So there's no way to get at, what does x have to be? There's no way to get at it because we have no idea what this stuff, again, we have no idea what this stuff is supposed to equal out to. So we cannot solve it. It's not an equation. Please don't call it an equation. Please don't say you're going to solve it. I'm going to find a way to start deducting points when people make that mistake. I mean, not a million points, but I got to find a way to reinforce this somehow. So anyway, there's your introduction to that. So expressions versus equations, I kind of get that distinction made. The next thing is, well, what's this rational stuff? Rational in a math class, rational comes from the word ratio, which means, well, like a fraction, right? Two numbers. Ratio has two numbers, so do fractions. So rational expressions basically means fractions. Doesn't quite mean fractions. Let me be a little bit clear. You see this thing here? That's a fraction, right? You recognize that. Good old fraction, 6/7. You see that? We're not going to call that a fraction. Why? Because it's got some kind of a weird x in there. We don't know what x is, blah, 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 blah. So this is what we mean by a rational expression. It's a rational expression means basically that it's a fraction and there's some kind of x going on in the fraction. Okay, so you can, of course, make them, really fancy and stuff. That would be another nice rational expression because it looks kind of like a fraction except it's got x's and it's not really you can't call it a fraction. It's not like it's 2/3 or something. Anyway, that's what we mean by rational expressions. And if it was a rational equation, it might, just have an equals and you have another rational expression over here. That's all rational equations means. Okay, so hopefully I've got some of these definitions taken care of. The thing I want to add here, and this is sort of a, what would you call this, a programming note or something, is over here where it says without factoring. This is a big simplification of this subject. Usually when you see this subject, it's a huge subject and you spend at least like a week or two on it at least. And it's because you have all these polynomials and the first thing you have to do is you have to factor them all. Well, we're not going to get to factoring until about week 3 or so, and then we'll start solving equations by factoring in week 4 or so. So we're not quite there yet with the factoring, so I'm going to skip out the factoring for now. And it turns out that even with this huge simplification, we're not going to factor any polynomials here. There's still enough here to make it worth looking at. And it's also kind of a natural extension from what we just did in A was solving some equations, and they had fractions in it, so there were some fraction moves you had to do, and we're going to need those same fraction moves here. So it's kind of it's a reinforcement as much as it is a preparation for the future. That's a pretty good motivation for the topic, I hope. So what we should do, of course, is we should start getting into it. So let's part A, adding and subtracting rational expressions. That's what these are. Again, they're not equations. We're not solving. They're rational expressions. We gotta add these things. Just add them. So, like I say, fraction rules are here to stay. So you remember when you're adding two fractions, you have to get a common denominator, LCD, lowest or least common denominator. And so you have to look at the 7 and you have to look at the x and say, what's the common denominator when I've got denominators of 7 and x? And actually, it's 7x is what it is. So I'm going to multiply the first, I don't want to say fraction. I'm going to multiply the first term, how's that, by 7 over 7. And so that's going to give me, what, a 35 over 7x. And then over here, I multiply top and bottom by x over x. And so that's be giving me a 6x over 7x. Notice that the denominators are now the same. So I'm counting 7x's, so to speak. I got 35 of them, add 6x of them. What you've got is, I'm going to write it in standard form, 6x plus 35. Put the x term first as standard form. And that's it. There you go. 6x plus 35 over 7x. The old common denominator trick. It's still with us. So if you have these rational expressions, you want to add them together, you want to combine them, fine. Get the common denominator. And what's that? Well, in this case, all we really got to do is multiply the 7 and the x together to make a 7x. The common denominator is 7x. So this one's times 7x, 7. This one's times x over x. You end up with this. Okay, cool. Now, let's go over, before we get to example 2, let's come over here. It says PS, how to reduce not. Okay, this is an extremely common error. And it would be good, as long as we're sitting here looking at these kinds of things, let's get this out of the way right away. Sometimes people look at this expression here and they say, you know what? I think I'm going to cancel those x's. And the question is, can you really cancel those x's? Well, if you did, what would this become? You'd cancel the x. That would now be a 6 plus a 35 over a 7, right? And wait a minute. Now you're thinking of maybe canceling the 7 as well. So 7 into 35. Okay, let's do that. So 7 into 7 once, 7 into 35 5 times. So what you would be saying then is that here's what we started with, right? So you canceled x's, you canceled 7s, and what do we got? Across the top, we got 6 plus 5 is 11. It's just a 1 on the bottom. So it's 11, right? Now, hopefully you're saying, wait, that can't be right. And I'll prove that it can't be right because I'm going to try to erase my orange here if I can. Ooh, boy, I actually did it. Okay, I got the 3. Put the 3 back. That's a 35. Okay. Before I canceled 7s, right? When I canceled 7s, I ended up with 11. Well, what if I don't cancel 7s? Now I'm looking at a 41 on top and a 7 on the bottom. Now 41 over 7 is not 11, is it? No, it's not. So that proves to you that canceling like this is a no-no. No, you don't do it. No, 9, yet. Nuh-uh, don't do it. No, do not cancel like that. And by the way, hopefully that looks kind of similar to what we were thinking up here when we canceled the x's, right? It's kind of one of these diagonal cancels like that. You cannot do those. No. Don't do that. So how do we look at this then for canceling? Well, if you wanted to try to cancel something, what you could do is you could say, look, let's split this up into 2 fractions like this, right? Which, that's where we got it from anyway, right? We had the 35 over 7x and we added the 6x over 7x. That's how we got this in the first place. So I'm sort of splitting this up into 2 fractions. So in this fraction, I can cancel x's. And in this fraction, I can cancel 7s, right? And that gets us back where we started. But notice this is nothing like an 11. It's not a 41 over 7. It's nothing weird like that. It's a 6 over 7 plus a 5 over x, which of course is where we had started in the first place, right? Up here. So the moral of this story is, please never cancel like this. No. The problem is this 7 is underneath the 35, but it's also underneath the 6x. And that's hopefully what I'm showing here when I say you could split it up into 2 fractions. In other words, I cannot cancel the 7 into the 35 because I can't cancel it into the 6. And same thing with the x. I cannot cancel the x into well, I can't cancel these x's because there's no x over here to cancel. If there was an x over here to cancel, I'd be able to do it. Maybe I should just kind of briefly. If I had a 6x plus a 35x over 7x, now I can cancel x's. If I canceled x's, because I'm canceling all three. One, boom, boom. I'm getting 6 plus 35 is 41 over 7. Now, the reason that works is if I didn't cancel the x's, I'd have a 6x plus 35x is a 41x over a 7x, and now you can certainly cancel the x's, right? So it's kind of all or nothing when it comes to canceling in these rational expressions like this. I'm not canceling the x here and here because there is no x here. I'm not canceling the 7 here and here because I can't cancel the 7 here. That's what I mean by all or nothing. And this is a good way to maybe remember it sometimes. You could split it up into two separate fractions if you wanted. And then you've got different canceling things going on in the two different fractions, right? So anyway, I'm trying to head off like I say, an extremely common mistake. I'm trying to head that off. Hopefully I have frightened you away from canceling x's like that. Hopefully I have frightened you away from trying to cancel the 7 into the 35 like that. Don't do it. It doesn't work. It won't work. So, where were we? Oh, we were just like adding things together, right? We needed common denominators. Let's see what this example looks like. Oh, we're going to need a common denominator so that we can add those two things together. Let's say we do that. So the common denominator of x and x squared is what? Well, you have to think of an x squared this way. What x squared means is, remember that means make two copies and multiply them. So what x squared means is xx, x times x. So this is kind of like a 5 over x plus a 6 over xx if you wanted to write it that way. And I think if you write it that way, or if you at least think of it that way, you say, well, this denominator has xx, this denominator needs xx. So I have to multiply top and bottom by x. So what have I got? I got a 5x here over x squared, plus I got a 6 over x squared. And now I'm ready to just add across the top 5x plus 6, and that's all over the x squared. Remember, when you add when you add fractions together, or in this case rational expressions together, the denominator just carries along. It's like a like terms thing almost. Make the denominators the same, and it's kind of like combining like terms. 5x over x squared plus 6 over x squared is 5x plus 6 over x squared. Okay, cool. Oh, we got another example right here. Okay, what's this one say? 5 over x plus 4 minus 3 over x. Okay, we need to figure out what the common denominator here is. What do we need to say here is that this is not going to work. Okay, you don't build common denominators by adding. You build LCDs through a process of multiplication. That's the first thing to keep in mind. So again, it's not like I can, add 4 top and bottom, right? You never do that when you're adding fractions. You never add top and bottom. It's always a multiply top and bottom. So the other thing to think about is that thing 2. Fraction bars are grouping symbols. And when I say they're grouping symbols, what I mean is that x plus 4 should be thought of as a group, as something in parentheses. It's an x plus 4. It's one x plus 4 object. So looking at it that way, you say, well, what are my two denominators then? I've got, this is just an x, this is an x plus 4. And so my denominator contains both an x and an x plus 4. So here I go. I'm going to multiply this one by an x plus 4 over x plus 4. That way this one has both an x and an x plus 4. And then this one we're going to have to multiply by x over x. And it kind of doesn't matter whether you put it in front or in the back. It doesn't matter. So now this denominator has both an x plus 4. Okay, we're ready to rock and roll. So across the top I got a 5x here over x plus 4 minus, and then here I've got 3 times x plus 4 over an x plus 4. Notice my denominators are the same now. That's what's good. My denominators are the same. I could just carry that one across. And let's see now here. I've got a 5x. Now remember, this is like distributing. This is like a negative 3 multiplying both of these things. So this would be a minus 3x, and then there'll be a minus 12, right? Because I have a minus 3 times 4 is a minus 12. 12. Okay. So what have we got here? Well, now I've got these two like terms to put together. So that would be a 2x minus a 12 over an x plus 4. And there's your answer right there. Now notice I'm not bothering to multiply this out, right? Leave the denominator factored. That's usually factored form is a highly desirable form anyway. So that says leave. Leave the denominator factored. Don't bother multiplying it out. You're just making more work for yourself, and it doesn't even look as pretty when you're done. If you want, you could. These both have 2's in them, so you could factor the top, and then everybody's factored, and everybody's happy. This is actually a really good form for your answer as well. Okay, but again, don't bother multiplying it. When you get the common denominator, don't multiply it out. Just leave it as its factored form. Just leave all the pieces there. Okay, let's take a look at this example 4 here. Ooh, we got 3 denominators. Wow. Okay, well, you got 3 denominators, you got 3 denominators. Here's the thing to notice. Again, the fraction bar is like a grouping symbol. So that's an x minus 2. You think of that as a single object, sort of. And again, you can't build common denominators by subtracting top and bottom. That doesn't work. It's always by a process of building up by multiplication. So I've got actually 1, 2, 3 different denominators. My LCD will have all 3 parts. So I might as well just write that out here. My LCD will be an x times an x minus 2 times a 2x plus 3. It's going to have all 3 parts to it. Every one of these has to have the same LCD, which has all 3 parts. So this 2 over x here, we're going to have to give it some parts, man. We're going to have to give it, let's see, it's got the x. It's going to need an x minus 2. It's going to need a 2x plus 3. Holy cow. So you multiply top and bottom by the x minus 2 and the 2x plus 3. Okay. This one here, plus x over x minus 2. But then we got to give it all of this stuff. Let's see now. Start over. This one's got the x minus 2. But what it needs is an x and a 2x plus 3. Top and bottom, x and 2x plus 3. Oh boy, this is looking hideous. And then we got, oops. And then we've got minus, and I've got this 1 over 2x plus 3 like this. Holy cow. Look at this mess. And it's got the 2x plus 3, but it needs the x and the x minus 2. Kind of put that in parentheses, I think. Okay, cool. Wow, a lot of stuff, huh? Well, the good news is the denominators are all the same. So it's x minus 2, 2x plus 3. That's the same denominator all the way across, right? Just looking at the denominator. X minus 2, 2. Okay, now let's put the tops together. I've got, well, how about if I start multiplying as I go? So this is like a 2x minus a 4. But then I'll still have to multiply by that 2x plus 3. Okay. Plus, now this is kind of like x times x is x squared, multiplying 2x plus 3. So x squared times 2x is a 2x cubed plus 3x squared. Okay. Minus. And then I got to distribute this. Now, keep in mind, this is a minus x. The minus goes with you. Minus x squared minus times minus is plus 2x. Did you see that? Minus x times minus 2 is a plus 2x. That's what happened there. Now, come on, you. Okay, there we go. So if we continue to simplify this thing, notice first we have to multiply this stuff together. Now this is something I'm sure you've seen before, so I'm not going to sweat it. I think you can do the FOIL thing, right? You remember this stuff. 2x times 2x would be a 4x squared. And then you got a plus 6x. Then the minus 4 times this is a minus 8x. Minus 4 times 3 is a minus 12. Remember that whole FOIL stuff? The first, the outer, the inner, the last. Basically, I always think of the 2x has to multiply both of these. And then the negative 4 has to multiply both of these. So you get 4 terms in the end. 2 terms times 2 terms is 4 terms. Anyway, continuing. Then, continuing with all this stuff, I got plus the 2x cubed and plus the 3x squared and minus the x squared and plus the 2x. And that's all over the LCD. Getting there. Okay, so what is this now? Like terms should go together. I've only got one x cubed, so I'll start with that one. By the way, when you go from highest exponent to lowest, that's called standard form. That's usually what you want to do. Now I'm going to look at all of the x squared terms. So I got 4x squared, 7x squared, minus 1, 6x squared. So that was a plus, right? Yeah, plus a 6x squared. Okay, now let's look at all of the x terms. 6x take away 8. That's a negative 2x. Oh, plus 2x. Well, the x terms cancel. That was nice. And then the only thing left is that negative 12. So there. And then on the bottom, we've got, I can put the LCD in there. And again, in this case, you really wouldn't want to, would you? Don't multiply this out. Leave factor. Don't multiply out the denominator. You do not have to do that. And in this case, that would be a little bit painful to do that. So let's just not. So I've got my numerator in standard form. That's a nice form for your numerator. And this is supposed to be an exclamation point. Leave the denominator factored. That's a good way to do these things. Now, I wanted to throw in an extra example before we get to the equations. This example isn't going to be quite as hairy as this one, I promise. This is about as good as it gets here. I mean, just be careful that you've got all the pieces for your denominators. Make sure everybody gets the right pieces. Be very careful about your negatives and stuff, especially over here, right? The negative had to change that minus 2 over here to a plus and stuff like that. But the other example I wanted to throw in here, please tell me I've had a spot. Here's a spot. I'll use this spot up here. I want to throw in one more example. So what were we up to? 4? So I'm going to call this like an example 4b, I guess. Example 4b. Now, I promise this one wasn't so bad. It's x over x plus 1 minus 2 over x plus 1 equals No, plus. I'm sorry, plus. We're not doing equations yet. Plus 3 over x plus 1. Now that's nice because they all have the same denominator already. They already match. It's all over x plus 1s. So that's my common denominator. So all I got to do is come across the top here, x minus 2 plus 3. Now x minus 2 plus 3 is actually x plus 1, right? Now here's a situation where we can cancel. But keep in mind, I'm not canceling... please keep in mind, I am not canceling these x's like that. No, I am not. And I'm not canceling these 1s. No, I'm not. Because you can't just cancel piecewise, right? Remember, this x plus 1 is kind of like glued together. The fraction bar is a grouping symbol. This is an x plus 1. And on the bottom, this is also an x plus 1. Okay, but those are the same. So anytime you have something over itself, it does reduce to just 1. So notice what I'm canceling is not the x's, not the 1s. I'm canceling the entire x plus 1 nugget. That nugget cancels into that nugget like that and makes a 1. Okay. So I wanted to have that there next to this one. So yeah, that's good. Good for you. Good for you. Okay, so we've been playing around with some rational expressions, adding them, subtracting them, that kind of stuff. Let's get some equations going. See how it says equations? That's because it's got equals. See, we got equals now. Now that we have equal signs, we have two sides. I have an expression on the left, I have an expression on the right, and they're equal to each other. That's called an equation. Now is the time that I can use the word solve. We're going to solve these things. And again, solving means what number do I have to use for x to make this into a true equation, a true statement, to make this work. To make this equation work, x has to be what number? Okay, so what are we going to do? Well, we're going to start the same way that we've been playing with our adding and subtractings. We're going to get a common denominator first. Now this 5 at the moment has like a 1 on the bottom, right? So you want to look at all three of these. You want to look at the x and the 3 and the 1 and say, what's the common denominator of x, 3, and 1? And hopefully you can see that that is going to be 3x, right? 3x contains an x, 3x contains a 3, 3x certainly contains a 1. 3x is the lowest product that contains all of those denominators. So I want to make everything into a 3x, or every denominator into a 3x. So that means that this fraction, rational expression, needs to be multiplied by 3 over 3. This one needs to be multiplied by x over x, right? Here I got a 3x, here I got a 3x. This one is going to have to actually be multiplied by 3x over 3x. And now I've got a 3x. So what are we looking at? We're looking at, this would be a 9 over 3x minus, this would be a 2x over 3x equals, and then this would be a 15x over 3x. So notice it's 3x all across the bottom. Now if it's 3x all the way across the bottom, you can just kind of ignore that. This is your equation right here. They kind of, in a sense, cancel. I suppose you could think in terms of, I'm going to multiply the entire equation by 3x, which is going to cancel that denominator, and that denominator. However you look at it, the denominators go away. So 9 minus 2x equals 15x. We are so almost done. Add 2x to both sides. Divide both sides by, now be careful here, you want to divide by the 17 on both sides, right? Trying to get x by itself. You want to cancel the 17s. Look at the x. I want to cancel the 17. So x is 9 over 17. Cool. That wasn't so bad, I guess. Huh? So it's kind of common denominators are here with us a little bit more. Okay, let's look at this one. What's my LCD going to be here? Well, I guess you could say the 0 is like a 0 over 1, right? 0 over anything, really. These are all equal to 0. 0 over anything. What you can't do is you can't do something like put a 0 on the bottom. That's undefined. You can't have 1 over 0, you can't have 2 over, you can't have 3 over, you can't have 0 over, you can't have any of these things. You can't have a 0 on the bottom. But a 0 on the top, no problem. So the LCD here is what now? Well, again, this is, a fraction bar is a grouping symbol. The x minus 2 is in a group. We usually get lazy and we don't write the parentheses, but they're there. So our LCD is going to have an x, right, because of this. And it's going to have an x minus 2 because of this, and the 1 is kind of there by default, I guess. So that's our LCD up here. So how do we change these fractions? Well, they're rational expressions. This one's going to need to be multiplied by x over x. That way it has both the x and the x minus 2. This one's going to have to be multiplied, I'm trying to squeeze it in here, by an x minus 2 over an x minus 2. And then this one's going to have to be multiplied by both x and x minus 2. So what do we got here? This term is a 2x over an x times an x minus 2. Plus, this term is now a 3 parentheses x minus 2 over an x minus 2. And this term is still 0 times 0, 0 times anything is 0. So it's still a 0 on top over x minus 2. All denominators match. Denominators don't matter anymore. There's our equation. So the goal really when you're solving these rational equations is to first get rid of the whole fraction thing. Get rid of all the denominators. Make them look like straight line equations. And you do that by first making all the denominators match, because once they all match, you can basically ignore them. Basically. So anyway, 2x plus this. Okay, so I got 2x. Let's distribute here. That's a 3x minus a 6. Okay, cool. So I've got a 5x minus a 6 equals 0. So if you add 6 to both sides, and then you divide both sides by 5, you're getting 6 over 5. 6 over 5. Cool. You ready for a couple more? Example 7. This strange looking character out front that looks like it was put in that special handwritten font. Yeah, that was a typo. I was fixing a typo, so that's part of the problem. I'll write in blue. That'll keep things straight. So anyway, we've got 3 terms here. One term minus another term equals another term. They're all rational expressions, but because of the equals, that turns this into a rational equation, and we can try to solve now. Now, as with when we were just adding and subtracting things together, we need a common denominator. Looking at all these denominators, this denominator has an x in it. That means my common denominator is going to need an x. It's got to need an x. This denominator has a 2 in it, which means my common denominator is also going to need a 2. And then look at this denominator. It has a 2. Well, I already have 2. That's good. But it also has this, and remember, the x plus 4 in parentheses is like a single chunk that stays like a single chunk. It's an x plus 4. X plus 4. Okay. So that's our LCD. Cool. Now we just got to take all these things and make sure they have the LCD. So my first term, 3x over 2 with an x plus 4. And now in order to get all my pieces together, I need to have a 2. I do have a 2. I need to have an x plus 4. I do have an x plus 4. I still need the x. So this thing has to be multiplied by an x over x. You're making sure everybody's got the same pieces, so to speak. Minus 3 halves times. Okay, let me try to very carefully erase this stuff. Okay, what do we got? We got the 2. We got the 2. Okay, cool. But we need the x, and we need the x plus 4, top and bottom. X plus 4. And again, you always build denominators through a process of multiplying things together, right? So it's 3 times x plus 4 on top. Okay, that takes care of that term. Equals 8 over x. Okay, and now we ask ourselves, what pieces is this one missing? Well, it's got the x. It's got the x. It needs a 2, top and bottom, and it needs the x plus 4, top and bottom. So there we go. Everybody's got a matching set, right? I got a 2, x plus 4. I got a 2, x plus 4. I got a 2, x plus 4. Isn't mathematical? Isn't math rhythmic? It's rhythmic, man. It's cool. It's groovy. It's wild. So anyway, now that all the denominators are matching, I can pretty near ignore them now and just look at the equation across the top. So reading across the top here, I got 3x times x minus 3x times x plus 4 equals 8 times 2 times x plus 4. Okay, here we go. 3x times x, well, let's just call that 3x squared, eh? Now this next thing, remember this is a negative here, so this is negative 3x times, well, okay, that doesn't look so good. Let me say it this way. It's like having a negative 3x. Negative 3x is multiplying an x. It's multiplying a 4. So negative 3x times x is a negative 3x squared. Negative 3x times 4 is a negative 12x. Boy, does that look hideous, huh? It does. But you can kind of see, hopefully you can see this, right? This is a negative 3x in front that has to multiply first the x and then the 4. That's where this comes from. Equals, and then over here, think of the 8 times 2 as a 16 already. So it's 16 distributing the x plus 4. So that's a 16x, and 16 times 4 is going to come out to a whopping 64. Cool. Now, the x squareds were making me a little nervous at first, but luckily they're just going to cancel. 3x squared minus 3x squared, poof. So I've got a negative 12x here on the left. I've got a 16x plus a 64 on the right. What am I going to do now? I'm going to subtract 16x from both sides. So I've got, this is what, negative 28x on the left equals a 64 on the right. And so my answer is First of all, it's a 64 divided by a negative 28, which is going to be a negative answer. Just put the negative in front, please. Don't leave it down there. That looks hideous. Hideous. Bring the negative out to the front. We should cancel stuff, too. I always try to reduce your fractions. What's a big thing that goes into 64 and 28? I'm thinking 4s. So 4 goes into 28 7 times. 4 goes into 64 16 times. I guess that's our answer right there. Negative 16 over 7. Cool. All right, and then one more example. Don't go away. This example is important. I put it there because it's important. So let me first kind of maybe shrink this. What'd you do? I'm going to try to shrink this stuff and kind of get it out of the way a little bit here. Oh, come on, you. Stay circled. Okay. Shrink. Come on, you're supposed to shrink. Shrink. There, see? I love that. I just love that. Okay, moving over to this one. First of all, you would want to ask yourself, what is my least common denominator? Looking at all the denominators, I see that I have an x minus 2 here, and remember those are glued. A fraction bar is a grouping symbol, which means that if you see an x minus 2 there, you should think of it as in parentheses, grouped, in other words. This denominator is x minus 2. This denominator is x minus 2. Oh, wasn't that lucky? Wasn't that lucky? So let's just kind of ignore those, right? And read across the top. 6 plus 3x equals 12. Right? That's all that's left up here. 6 plus 3x equals 12. Cool. So I guess this won't take too long. Subtract 6 on both sides, right? And then divide both sides by 3. And I'm getting x equals 2. So, why did I ask you not to go away? I asked you not to go away because that's not the answer. There is no solution to this problem. What's the problem with this problem, you might ask? Well, the problem with this problem, I will answer, is if I were to try to use x equals 2 in my equation, remember that's what a solution is supposed to do. A solution is supposed to give you a value that you can plug in for x, and then the equation works. Well, the equation is not going to work if I plug in x equals 2. Why not? Well, look at this term. This would be a 12 over 2 minus 2 is, dividing by 0. Not allowed. Remember, you can always have a 0 on the top. That's fine. 0 over 12 is 0. But dividing by 0, that doesn't work. Remember, dividing is like how many times does 0 go into 12? 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. You can put 0 into 12 without you get into an infinite loop. Your computer crashes, your Excel says your calculator says something, I don't know what, syntax error, I don't know what it says. It doesn't work. So if you can't plug it into the equation, that means that you can't call it a solution, and since you can't call it a solution, you say there is no solution, because the only solution I was able to find was 2, and then I wasn't able to use it, so I can't even use it. So there is no solution at all. Keep your eye out for that possibility. So with this one, really, I got negative 16/7, and what I should have done, and actually what I did without saying it, is I spot check and say, if I were to plug in negative 16/7, would that make the denominator 0? Heck no. What if I plug the negative 16/7 here? Would that make this denominator 0? Heck no. What if I were to plug in 9/17 to this denominator? Is that going to make the denominator 0? Heck no. Usually it's not going to be a problem. It's just every now and then you're going to get a solution which you have to throw away. So you got to spot check at least. Say x equals 2. Can I use that? Oh, I can't. Oh my gosh. This is one of those problems. I can't use the 2. So don't use the 2. No solution. I would say that was a pretty good introduction to rational expressions, rational equations. It's most of the stuff that you need without the factoring. So later on in the course, like weeks 3, 4, we'll ramp this up a little bit. You'll have expressions and you'll have to factor them first to figure out what is the common denominator and so on. But that's later. Don't worry about that now. Just go have fun with this homework. Yeah.